Welcome back to AP Calculus BC. We are in the midst of Topic 2, our series convergence tests. We finally actually got a series convergence test last class where we learned about the nth term test for divergence and also the harmonic series. Today we're really going to start the pattern of getting a new convergence or divergence test really every day for the next 6 or 7 days. There are a bunch of them, and at the end you'll get a nice summary sheet and we'll try to reuse them a bunch of times so that you stay comfortable with it. But let's go ahead and get into it. We are going to start with an opener where f of x is a continuous, positive, and decreasing function. Now, those are three terms that we're going to come back to often today. So I think what we should probably do is explore functions. No calculus necessary yet. Explore the types of functions that meet those criteria. Notice I say for x greater than or equal to 1. Your goal is to try to draw an example of this function, so what would a graph look like? And then also write 3 equations that meet those criteria as well. And you can use your calculator if necessary. And then you can go ahead and answer the 2 questions down below. So go ahead, please, try that, and then once you're done, unpause this and we'll come back together. Alrighty, well, graphically, since we're only dealing with x's greater than 1, greater than or equal to 1, and we have a positive above the x-axis, decreasing negative slope, continuous, don't pick up your pencil, function, then I think we're probably looking at something that looks like that, right? I'll put a little arrow at the end. Now there's a lot of equations that look like this. One of them would be the easy equation 1 over x, and you should note that the graph of 1 over x isn't actually positive, decreasing, and continuous everywhere. In fact, it's none of those 3 things at every point on the graph. Over here we have a decreasing and negative graph. We have a lack of continuity in the middle, but this function does meet the criteria for x greater than or equal to 1. And so that's something we'll come back to today as well. It doesn't really matter what this function's doing to the left of 1 or to the left of whatever our starting point is, as long as it meets the criteria from whatever x we start at and move on, then we're golden. What are some other functions? Well, you could think of the function 1 over e to the x. Right? There's nothing wrong with that function. E to the x is positive, 1 over e to the x is positive, never going negative, no loss of continuity. And we could even look at another one. What if we did like 1 over the natural log of x? And you might remember, well, wait, the natural log of 1 is 0, and 1 divided by 0 isn't continuous. You're right. Everything after that is continuous. So what if I just like, I don't know, let's shift it maybe left 1 or something like that. So if I shift it left 1, we could do something like that. And I bet that would probably work out. No, that wouldn't work out, would it? So maybe we can do something like plus 2, or either way, you get the idea. That might not actually be continuous everywhere, but eventually it's going to stay positive. Nothing bad is going to happen. Cool. Now, as f of x is positive but always decreasing, one thing we know about the graph of f then is it is eventually going to be approaching an asymptote. A lot of times it's going to be approaching an asymptote of 0. It could approach something above that, that's fine as well, but there has to be some sort of asymptote, and in particular it has to be a horizontal asymptote. Okay. And then last but not least, and we'll come back to this a few times today, what type of Riemann sums over approximate versus under approximate? Well, I never have this memorized. I just write it out and we take a look at it. If we look at my first subinterval and I start on the left side for my left Riemann sum, you can tell that a left Riemann, and sometimes you'll see this as LRAM, right, the left rectangular approximation method, is going to over approximate, which of course is going to mean that my right rectangular will under approximate. But just to double check, if we start on the right side, yeah, definitely under approximates. Okay. Now, what are we trying to do? Well, our goal for really every day for the rest of this unit is when I give you a series, you have to tell me if that series converges or diverges. Last class we saw a proof that the harmonic series, right? What is the harmonic series again? All right, that's the one where it's 1 plus a half plus a third plus a fourth and so on and so forth diverges. And that proof used integration. And so today we're actually going to extend that idea, that integration we did last class, even those Riemann sums, to a more general subset of sequences. In particular, those sequences which are positive and decreasing. Notice I didn't say continuous here because sequences aren't continuous, right? They only have inputs of the natural numbers, so there's just individual points. However, if you looked at the function that ran through those individual points, you'd have a continuous function. So here we go. What is this test? Well, the test is, again, very creatively named, because everything we do is creatively named in math. It's creatively named the integral test. And the idea behind it is that a left Riemann sum is always going to over-approximate our continuous positive decreasing function, while the right Riemann will always under-approximate. This test is not going to tell us the exact value of the series. Really, we need to get away from thinking we're going to know the values of the series. For pretty much all of these, we will not know the actual value. We're not going to know what the series sums up to be. We're just going to be able to tell if our series converges or diverges. The exact value of our integral is really going to be between the right Riemann sum and the left Riemann sum. And there's going to be a proof in your book on page 633 if you want to see a nice proof of the integral test, but for now I think we're just going to go through it. So here we go. Given some sequence, not the series yet, just the sequence, just the pattern, a sub n, which is eventually positive and decreasing, then consider the function a sub n represented as an actual continuous function instead of just the sequence. F of n has to be continuous, positive, and decreasing. We're going to come back to that a bunch. Assuming a sub n is positive and decreasing, then we know one of two things. We know that our series, the sum of the sequence, is going to diverge, not add up to a specific number, if, so IFF, if and only if the integral equals positive or negative infinity. You could also say that the integral diverges. You could also say the integral does not exist, something like that. Basically, if you don't get a numerical answer from your integral. And we also know that the series will converge. It will add up to a sum number like 12 or 4/7 or something like that, if and only if the integral is not equal to infinity. So basically that means the integral exists or it equals a number, something like that. Now, because these conclusions are if and only if, then we can read them forwards and backwards. So if they tell you that this integral is infinity, then we automatically know that the sequence diverges. Okay. Second, and we'll hit this over and over again today, the value of the integral is not equal to the value of the series. So whatever this integral equals here, if this is 12, this will not add up to 12. It tells you it converges by getting a value, but because this summation is going to be closer equivalent to Riemann sums, and Riemann sums are not equal to the value of the integral, we'll go more into this at the end of the lesson today. This value is going to be not exactly equal to the integral, somewhat close, but not equal. Okay, and then last but not least, you really should start your integral and summation from whatever value of n your sequence starts to fit the definition of positive and decreasing. So let's say like the first two terms right here, let's say for term 1 and term 2, a sub n is negative, and you're like, but we're only allowed to use this for a positive. Well, if once you hit 3, everything's positive, then do your integral and everything from 3. Because we know from last class that a finite number of terms, let's say the first two terms here, isn't going to affect if a series converges or diverges. So we're basically going to say, well, if we're negative for the first couple, but eventually it fits it, we'll start it at like 3, and we'll go from 3 to infinity and look from there, because then we're just adding on the two terms before, and that won't change your convergence or divergence. Okay, now in order to use a test for convergence on the AP exam, you do need to justify why you're allowed to use that test. You can't just jump into it, because otherwise you might make some false conclusions. For example, you certainly shouldn't be using the integral test on the sequence a sub n equals n squared, because if you picture the sequence n squared, right, and we'll just start with 1 if you want, we get 1, 4, 9, right? This is n equals 1, 2, 3, and we're just squaring each one. Quick sneeze. We're just squaring each one. if this is my sequence, then if I want my series is going to be 1 plus 4 plus 9 plus 16. I mean, those numbers are getting larger and larger. If you add up an infinite number of numbers that are getting larger, I'm pretty sure this series is going to diverge. And we could have seen that initially because we know that the limit as n approaches infinity of n squared diverges, right? That's our nth term test, or actually maybe I should say is not equal to 0, because our nth term test for divergence last class said you should always test your sequence formula. Your sequence formula has to go to 0. If it doesn't go to 0, the sequence automatically diverges. So there are a few steps to using a test for convergence. The nice part is step 1 is always the same. Use the, I'll call it the nth term test. You could always call it the divergence test too, to see if the series diverges. And honestly, I usually just do this in my head. I say, if we plug in infinity, do we get 0? No? Cool, we get to stop. As long as, and what we want here is we want to find that the limit as n approaches infinity of a sub n equals 0. Once this happens, we can continue. Now, here's where you have a tough dilemma at hand. We're going to learn about 7 or 8 different convergence tests, and they all are used at different times. Sometimes you can use multiple, but not always. So you're going to have this, this litany, this arsenal of convergence tests, and you have to pick which one you want to use. Now, sometimes you're going to try one and it just won't work. And you're like, drat, we'll try another. So you do, though, have to explain why you can use that test. And usually there's some initial conditions you have to meet. This is one of them for every test, right? We can proceed because the divergence test was inconclusive, indeterminate. And for the integral test, you do actually have to state that you can use the integral test because the function f of n, based off of the sequence a sub n, is continuous, positive, and decreasing. If it's not one of those three, then the integral test isn't actually going to give us enough or the correct information always for our sequence. Again, it's going to be based around Riemann sums, and if your function goes positive and negative, Riemann sums get weird. If it's not always decreasing, things get strange. So we really only use the integral test if your function does those three things. So let's try a couple examples. Looking at each of these, we're going to decide if the series converges or diverges. I'm telling you right now, you're probably going to want a separate piece of paper for these three. I think I'm going to have to write really small, and I still might run out of room. But let's take a look. Okay, so our first one, again, that nth term test for divergence, I'm going to go ahead and just think about it in my head. We can write it down on the side, why not? So the limit as k approaches infinity of just the formula for the sequence, k over k squared plus 1. Think of, sorry, doing too many things at once. Think of your dominant, so k over k squared, which is the limit as k approaches infinity of 1 over k. 1 over infinity is 0. Cool. There is a chance this series might converge. Yippee-yay. You'll actually notice that on all three of these, you're going to get 0 every time, so I won't do it again, but you should. I mean, this whole denominator will become infinity, 1 over infinity, 0, 1 over infinity, 0. So the nth term test for divergence gives us an indeterminate form. That's actually a good thing, because if we didn't get 0, it is very conclusive. It tells us that they would all diverge. And there will be a couple on your assignment tonight that will diverge. So check that ahead of time to save you some work, because man, is there ever some work. All right, now I'm going to launch into the integral test. However, well, I guess we should probably do it well. So let's go ahead and think of this function. So we're going to say as f of, and you could use k here, n, whatever sounds good to you. You can use x, I'll use x, right? As f of x equals x divided by x squared plus 1 is, and then as we write these out, we should probably think if they're true, is continuous. Is this continuous? Sure. The denominator will never become 0. We can't square something and get a negative. Continuous, positive. Will it always be positive? If we start at 1, sure. There's all addition on here. It'll never become negative. And decreasing. Well, what's the quickest way to see if something's decreasing? Just compare the numerator and denominator. right? To me, because you're squaring something here, the denominator is going to be really big, okay? And the numerator is going to be small. And what's going to happen is if you have small over big and things are getting larger, you're always going to have small over big, but the big denominator is going to dominate the numerator, and it's going to get way bigger than the numerator. So we're going to have small over bigger, and then bigger, and I'm sure that's a word, and so on and so forth. So I think this fraction is definitely going to decrease, right? We have some numbers 7 over 10, 7 over 50, 7 over a million. Think about those fractions. They are getting smaller. They're approaching 0. So definitely decreasing. Then we can apply the integral test. Okay, so let's apply the integral test. And I'm already almost out of room, and I'll need a lot more room. So you'll definitely want a separate piece of paper. But here we go. We are going to take the integral from 1 to infinity, y1, because it's over here, of x divided by x squared plus 1 dx. I'm not even going to start this over here. Let's go over to the side. So in problem 1, we're doing the integral from 1 to infinity of x divided by x squared plus 1 dx. We actually need to take this integral. Before we do that, though, we're of course going to remember our correct notation here, right? We do need to replace our infinity with an actual variable. This is our improper integral, right? Everything's coming together, very exciting. I think we could probably do a u substitution here. I think that'd be just fine. We're going to let u equal the denominator, and I think that's going to make du equal to 2x dx, but I don't see a 2x dx, I just see an x dx. So we get 1/2 du equals x dx. We also need to replace the limits of integration. So we'll need to find u of 1, which is 1 squared plus 1. 1 plus 1 is 2. Then we're also going to have to find u of b, which is b squared plus 1. Just b squared plus 1. Easy enough. So, new integral. Well, what stayed the same? That stayed the same, that stayed the same, and that's really about it. Denominator becomes u. We got 1/2 du. And then our new limits, we have 2 to b squared plus 1 with the limit as b approaches infinity. Nifty. Simplifying just a little bit more, the limit as b approaches infinity. Let's actually just factor out the 1/2 from everything. I think that'll save us a bit of time. And then we have the integral of 2b squared plus 1, 1 over u du. Nice. Okay, working on through. 1/2 times the limit as b approaches infinity. We have our bracket, natural log, absolute value of u from 2 to b squared plus 1. And then we can start substituting things in here. We get 1/2 the limit as b approaches infinity of what? Well, actually, let's even move this inside now, because this is going to be the natural log of b squared plus 1 minus the natural log of 2. But take a look here. This piece diverges. Because I know that when we substitute an infinity to a natural log of infinity, picture the natural log graph goes up forever, is infinitely large. So as soon as we get this, we get that this diverges. Okay, we found the integral diverges. Are we done? No, because this question asked us about the series. So I'm actually going to jump back over here and finish this off. So we found that this diverges. Okay, you would have to show the work in the middle, but here we go. So as the integral from 1 to infinity of f of x dx diverges, then the sum from k equals 1 to infinity of k over k squared plus 1 also diverges. Basically, they share the same end behavior. If we had found an answer for one of them, then the other one would converge. Because we couldn't find an answer, it diverges, right? Nothing too terrible at all. Now, again, you should do this preamble every time. I'm going to try to save a bit of time and maybe a bit of paper and really just do the integral here. It's nice practice, and we can go from there. So let's go ahead and take a look at our next one. We are going to find the integral from 3 to infinity of 1 divided by, let's do 2k minus 5 to the 1/2 power. Oh no, let's use x here since we're 2x minus 5 dx. And actually, I bet we could even do this one without a u substitution. A u substitution might make this a little bit easier, so there's nothing wrong with using one, but I bet we can reverse engineer it without one. So let's take a peek. So this is the negative 1/2 because we brought it up, right? And then I think our antiderivative then, the limit as b approaches infinity of, well, we're going to add 1 to the power. That's positive 1/2. We need something to cancel out the 1/2 so it matches what we had over here. That's 2. And then we think, well, if I take the derivative of this, does it get me this? I don't think it does. I think the 1/2 comes down, it cancels. That looks good. We get this to the negative 1/2. But then the chain rule multiplies by an extra 2 out here, which is a no-no. I don't want the extra 2. We need to somehow cancel out that extra 2. So I could put an extra 1/2 here, or I could even multiply the 1/2 by 2, and I think that'll actually probably be correct from there. 3 to b, and I missed the b up here. So double check it. If you take this derivative, my guess is you will get this, because this 1/2 will come down and cancel out the 2 that comes out from the chain rule. But again, you can use a u substitution too. You'll get the same thing. Nothing bad. Okay, so then we're going here, and we are going to need to substitute everything in. So we have the limit as b approaches infinity of the square root of 2b minus 5 minus the limit as b approaches infinity of 2 times 3 minus 5. Oh, sorry, and I don't know why I did a limit there either. Come on, Mr. Grant. Of 2 times 3 minus 5. Well, you should know your square root function. Your square root function goes up to infinity, kind of like that natural log or a log function. So again, this piece will diverge. So I always like to say at the end this diverges. And you'll notice I avoid using an equal sign. Equals means that they are equal to each other, and we usually only use equals with a value. So if we're getting divergent or infinity, I really try to avoid using that equal sign. We can say it diverges, and then we're fine. From here, we need a conclusion. The conclusion is identical to what we did over here with other functions. As our integral diverges, then that also diverges. Okay, let's go ahead then and take a look at our last one. Our last one, we are again going to need to do an integral from 0 to infinity of 1 over 1 plus x squared dx, which is the limit as b approaches infinity, 0 to b, 1 divided by 1 plus x squared dx. This one we just need to know. I think this one is going to be our inverse tangent, right? Remember our derivative of inverse tangent? So I think this is just going to be arctan or inverse tangent of x from 0 to b. Okay. The limit as b approaches infinity of the arctangent of b minus the arctangent of 0. We need to know both of these values. And this one is a little bit trickier. It might help you to remember what the graph of inverse tangent looks like. We talked about this one other time, but because regular tangent is bounded between negative pi over 2 and pi over 2, these are your vertical asymptotes, then when we do inverse tangent, it's going to be bounded between, it's going to look like this, right? It's going to be bounded between those same asymptotes, just flipped around. So when we look at an infinity, you'll notice that you're approaching pi over 2. Also, you can see that 0, 0 is common to both of these. So that means that we get pi over 2 at infinity here and 0 here. So we get pi over 2. That's awesome. We actually got a value here. Cool. Well, what do we do with that value? We use it to conclude. So as the integral from 0 to infinity of 1 over 1 plus x squared dx equals pi over 2, then the sum of k equals 0 to infinity of 1 over 1 plus k squared. Did I use n up here? I did. Oh well. They will not care if you change your variable here. Converges. Okay. Easy enough. Don't say it equals pi over 2. These are seldom, if ever, actually equal to each other. It is somewhere near pi over 2, but we're actually going to cover that right now. So we saw a couple cases where we got divergence. We saw one case of convergence. Let's go ahead and see if we can estimate that sum to finish off for today. Okay. We don't need to know too much about this. This is probably way more than you need actually, but it did come up once on the AP exam, and I always like to make sure we've learned everything that has come up and can come up on the AP exam. So this is also a nice reminder of summations of sigma and rectangular approximations. So here we go. We're going to be given that the integral below of a positive continuous decreasing function converges to some value L. When I say converges, I mean there's actually an answer. We didn't get divergence like our first two up here. So let's look at a graph of that. Okay, here is my graph. Okay, nothing terrible. Starting at 1, go from there. Now imagine we wanted to find the left rectangular approximation for this function, starting on the interval from 1 to 2, right? We're just going to use each of the sub-intervals that I have here to find an approximation. Well, I drew this in for you on your paper, but I can redraw it here. So we use the left side of the interval to create our rectangle, yeah, and so on and so forth. Now, if we actually wanted to find the area of this rectangle, of course, the base on all of them is 1, right? I did all those 1s down here. I was pretty proud of my little clip art skills. But either way, the base is clearly 1, which is why when we find the approximation, right, we add everything up. We do base times height. All these 1s are just the bases. To find the height of this rectangle, it is, of course, the distance from the x-axis up to the actual function. And so that is basically the value found when you plug 1 into the equation for your function, f of 1. So to find the area of this first rectangle here, it is the base of 1 times the height f of 1. It's the height of the left x coordinate for each one. So our next one is going to be a base of 1 and a height of f of 2, and so on and so forth. Now, of course, the 1s don't really matter, so it really just ends up being f of 1 plus f of 2 plus f of 3 and all that fun stuff. You should actually notice that that's the exact sum of the series, though, because to find the sum of the series, they're using a sub n. A sub n is the same formula as this graph f of n. Right? F of n uses every value to a continuous function. A sub n only uses 1, 2, 3, 4. So a sub n really is f of 1 plus f of 2 plus f of 3. And so you'll notice that this sum right here is actually equivalent to the left rectangular, left Riemann approximation method. And since this is clearly an over approximation, right, we can see our extra little pieces here then that tells us that the sum of the series is actually greater than the integral. And I'll try to highlight what I mean here, right? And I'll show you in some colors right now because that can be a little confusing. The integral is, of course, just the exact area underneath this. This is the integral that I've done in blue, right? It's the exact area underneath. Versus we just showed that this sum of the series is actually the same as the left Riemann or left rectangular approximation method. And clearly when you do that, you get these extra pieces. So the sum of the series has to be bigger in this case, or in any case using the integral test, of the actual sum of the integral. So again, jumping back to what we just did over here, if we found that the integral is pi over 2, this is the left rectangular approximation method, we know that this is going to be larger than pi over 2. Well, how much larger? Because that's tricky. I mean, is it infinitely larger? Is it 1 larger, 0.5, pi? Who knows? Well, we're going to get a better indication when we do the right rectangular approximation method. So same idea, but now notice when we create our rectangle, the height is dictated by the right x coordinate. So when I find the right approximation, it's going to be f of 2 plus f of 3 plus f of 4. And this is, of course, going to be an under approximation. So it shouldn't shock you too much that this right here is equivalent to the sum, not starting at 1 this time, starting at 2 of our sequence, right? So we're starting at 2. And clearly, if we start at 2, it still approximates the area for the integral, which starts at 1, right? We're just leaving off the 1 here. So it tells us that the sum starting at 2 is actually less than the integral. Okay, but notice if we add on the term a sub 1 to the series above, we actually get our original series, don't we? If we take this guy and say, well, that is almost our series, but aren't we missing the first term? So let's add on the first term. Okay, doesn't that give us the original series here? And so we can actually use a little bit of algebra and manipulate this fact. So we saw that our right rectangular sum is less than the integral. It under approximates. We're going to add a sub 1 to both sides. We're allowed to do that. And so then this gives me the sum of my series is less than the integral if you add on the first term. So if we put everything together then, and this is a little bit tricky, it takes what we did right here. What we did right here, it's telling us the sum of the series is less than the integral plus the first term. But also, the sum of the series is greater than just the integral. We can get this trifold relationship here that tells us that the integral, or rather, the sum is greater than the integral, but the sum is less than the integral plus the first term. And that actually allows us to bound our sum and get a pretty reasonable approximation for the answer. It's not going to be perfect. It's somewhere in between there, but that's not bad because we found on the practice problems on the previous page, we found this answer. That's just calculus, right? And we found this answer. That's just calculus. And then a sub 1 is just the first term of the sequence. So if we find the answer to the integral and the answer plus the first term, we can set up a relationship here that will tell us what the sum is in between. Now this only works for functions where the integral test applies, which are what? Oh yeah, functions that are continuous, positive, and decreasing. So the bookwork problems then are actually going to be a little bit different than the directions in the book. So you do need to use the integral test on each of these problems here, and you need to state the conditions, determine if it's and determine if the series converges. But then the second part is if the series does converge, you do need to determine an interval bound, that's up here, that your sum lies between. So I'm actually going to go ahead and demonstrate problem 21. I do have all of my answers in my work, and notice there is quite a bit of work here. As always, I go through a little bit more than you need to do, but I'm going to go ahead and take a look at this guy over here. If you don't want to listen to me talk through this, you can totally end the video now and start working, but let's see what we can do here. So they want us to do two things. So n equals 1 to infinity of n times e to the negative 2n squared. All right, so I want you to do two things. The book only wants you to do one. The first thing the book wants you to the only thing the book wants you to do is to decide, does this series converge or diverge? And then we're going to have to do the second thing, our special thing for this, and say, okay, cool, we found it converges or diverges. This one will converge. What is the sum bounded by? So let's begin. I always start with not the integral test. You should actually just say, well, I don't know if I'm going to use the integral test yet, so we're going to start with not the integral test. And my not the integral test is I'm going to find the limit as n approaches infinity of n, and I'm going to move this guy down, negative exponents or gross, e to the 2n squared. Okay. Well, this to me looks like dominance, and I know that e to a power is much more dominant than n, so I'll just rewrite it like so, and this is going to be 1 over infinity, which is 0. Cool. Nth term test for divergence is inconclusive. It means we need to do more. Indeterminate, we got 0, though. If we didn't get 0, we're already done. That's the entirety of the problem if it's not 0. Nth term test says the series diverges. Cool. The next part is I need to make sure that this is positive, continuous, and decreasing. Now again, I just write it out. You don't actually have to prove it to them. So I'm just going to say as n divided by e to the 2n squared. No, I don't like that. Sorry, let's use x. As f of x equals x times e to the negative 2x squared is continuous. Well, is it continuous? I think so, because e to a power, any number to a power, I think 2 to a power, that can never be 0 and never be negative, so that's easy enough, is continuous, positive, we just discussed, it can never be negative, and since we're starting at 1, the numerator is always positive too, and decreasing, Will this be decreasing? You could write out a bunch of terms if you would like, but think about how much larger the denominator is than the numerator. Write out a couple fractions where the denominator is way huge and the numerator is small. They're going to get smaller and smaller and smaller. So, and decreasing. Then we can apply the integral test. Right, we just did a couple of these, nothing too terrible. In case you're curious, this is all like part A. So we're going to go through and we're going to find, and I'll skip ahead because I know we're going to do the limit as b approaches infinity, the integral from 1 to b of n over e to the 2n squared dx. And I should be using x through here. I don't know why I keep switching back to n, but that's all right. Okay, well, I think this will definitely be a u substitution moment. We're going to go through, we're going to say let u equal 2x squared, which means that du is going to equal 4x dx, which means 1/4 du will equal x dx. That's going to take care of this over here. We need to rewrite the exponents, or not the exponents, the limits. So u of 1, what is u? 2x squared, 2 times 1, which is 2. And u of b is just 2 times b squared, 2b squared. Cool. Here we go. The limit as b approaches infinity, the integral, this part didn't change, the rest will. It becomes e to the u, and then we said that this is 1/4 du. My new limits are 2 to 2b squared. Looking pretty good so far. And then I'll work sideways to save some space. I'm going to factor out the 1/4. Be irrelevant till the very end. B approaches infinity of 2 to 2b squared. That was gross, should have done better. 2b squared. And then instead of 1 over e to the u, let's bring that up. Something like that. That looks pretty good. Yeah. All right. From here, we can probably do this antiderivative. Be careful with that negative u. I maybe should have left all of this up here, but that's okay. So as we go through, we get 1/4 times the limit as b approaches infinity, antiderivative time. E to the negative u is itself, but then think if you take the derivative of this, does it match? No, it'll be off by a -1. We need an extra negative in here, but again, I'm going to be a little sneaky, and instead of writing this negative inside, I'm going to actually go ahead and factor it out front so I don't have to deal with anything weird. And then we're going from 2 to 2b squared. All right, so -1/4, and then we start to plug everything in. Don't forget that e to the negative u is the same thing as 1 over e to the u, and I'm going to use that when I evaluate things here. So the limit as b approaches infinity of 1 divided by e to the 2b squared, no negative because we move the exponent back down to the bottom, minus 1 over e squared. Okay. Hopefully we can see that when we substitute infinity in here, the whole denominator becomes infinity, the whole thing goes to 0. -1/4 times negative e squared is 1 over 4e squared. Whew, that was a ton of work. But we did get an actual answer. We didn't get divergent, so we should probably write our conclusion. Okay, so as the integral from 1 to infinity of x over e to the 2x squared dx. You can just say converges. You can say equals 1 over 4e squared, whatever sounds good to you. Then the sum from 1 to infinity of n over e to the 2n squared converges. You could say by the integral test. We already used the integral test up above, whatever sounds good to you. That's all we need for A. B goes a little bit quicker. Part B says, cool, you told me that it converges. Can you tell me what that sum is going to be? Well, the sum is actually a pretty easy one here. The sum is going to use the fact that the integral, right, from 1 to infinity of x over e to the 2x squared dx is going to be less than the actual sum from 1 to infinity of n over e to the 2n squared. But that in turn is going to be less than the first term plus the value of this integral. Well, I think we actually know pretty much all of this. We know, of course, this integral comes out to be 1 divided by 4e squared, so that's easy. 1 divided by 4e squared is going to be less than whatever my sum is, okay? And divided by e to the 2n squared. And in turn, that needs to be less than, well, what is the first term? I don't think we actually found that. Well, up here, or even over here, we can, I think, quickly find the first term. If we have this general term of e to the 2n squared, and we start plugging in the first term, it's going to be 1 over e squared, I think. Yeah, that's easy enough. 1 over e squared. So 1 over e squared plus, oh, here's this integral value we already found before, 4e squared. And of course, we can clean this up just slightly. We can say then that the sum is in between 1 divided by 4e squared, from 1 to infinity, and over e to the 2n squared is less than, well, I think we probably should give this common denominators, shouldn't we? 4 plus 1, I think, is less than 5 over 4e squared. That's as far as we need to go. That gives us a nice bound on this sum. It tells us what we're in between here, and we should be good. So good luck with the other 5 or 6 problems. It is a little bit of a longer one just because we have to do this, but it's nice. It's really going to give you some integration practice so you don't lose those improper integral skills. And then we're also practicing bounding a little bit, which we'll need by the end of this semester. So thank you for tuning in, and I'm excited to see you back tomorrow for our P-series test.